Hello and welcome back to Probability Theory. And as always, first I want to thank all the nice people that support this channel on Steady or PayPal. Now in today's part 6 we will talk about the hypergeometric distribution. It's the name for an important probability measure we find for discrete cases. And here we will talk about the general formulation for it, also called the multivariate hypergeometric distribution. Here you can immediately keep three important ingredients in mind. First, the size is given by a natural number n, the sample is unordered and without replacement. Hence, a useful visualization is again given by an urn model. This means that in this model we take out n balls from the urn and look what we get. So we don't have an order and we don't replace the balls. Therefore, in short, you could say we draw n balls at once. And there you should see, this is only interesting if we have different colored balls in the urn. For example, we could have 4 different colors here. Hence, our first question here is, how can we mathematically formulate this? First, we can say that the different colors are just given by a finite set we call capital C. In our example here, we could just index the colors, so we choose numbers from 0 to 3. Of course, every set with 4 elements would do the work, but working with numbers is much easier for calculations. Also here in our simple example we could talk about possible outcomes, maybe in the case that n is equal to 5. One possible sample could be this one, where we have 2 green balls, 1 red ball, 1 blue ball and 1 orange ball. We don't have an order, we can just count how many balls of each color we have. Hence, in mathematical terms, here we would have a function from the set of colors C into the natural numbers including 0. And there you see immediately it's very helpful to index the colors with numbers. Because then we can rewrite this function into a tuple with 4 coordinates. So in this example here we would have 2 green balls, 1 red one, 1 blue one and 1 orange one. So what we always should have is that the sum of all these numbers is equal to 5. Then this could be a possible outcome of our random experiment here. Okay, now with this knowledge we are able to write down the sample space omega. It's simply the set of all functions or tuples of this form. So in general we would say we have numbers kc, where the lowercase c goes through all the colors in the set C. And then we say this is an element of the natural numbers including 0 to the power c. So this is a general notation of all the functions from the set C into n0. It's a helpful notation because it reminds us that we can also rewrite the function as a tuple. And we also put that into this notation here. Okay, and now the only condition we have here is that all these numbers add up to n. So we can simply write sum of kc is equal to n. And then we have our whole sample space omega. Of course, you already know, as for all discrete cases, the sigma algebra is just chosen as the power set of omega. Therefore, we can immediately go to the probability measure. And maybe also for this, it's helpful to first look at our example here. For our example, we already know we have tuples of 4 elements. Hence we can say we have k0, k1, k2, k3 from n0 to the power 4. And also the sum should be the sample size n. Now you might already see, for calculating the probability of an outcome, we have to know how many balls of each color are actually in the urn. For this we have to introduce new variables. Hence capital N with index C stands for this number. And then of course the total number of balls in the urn is given by the sum of all these numbers. Here we will simply use the symbol n for it. Okay, now by knowing all this, we can start calculating probabilities. As always in discrete cases, knowing the probability mass function is enough. Hence we just calculate the probability of a singleton. Now here we just have to count all the possibilities we can have. And then we will have a fraction here. Okay, we already know what's in the denominator because there we find all possibilities to take n balls from capital N ones. So we simply have capital N choose lowercase n. Okay, then for the next step you should see we want exactly k0 green balls. So we simply have n0 choose k0. And of course we have the same thing for all the other colors. Therefore in the next step we have times n1 choose k1. And then times n2 choose k2, times n3 choose k3. And with this we have our probability we call the hypergeometric distribution. Therefore in the next step let's formulate this in the general case. Also here we just give the probability mass function, so we put in a singleton, which we describe as before as kc. Then now you know we find a fraction where in the numerator we find the product of all the colors. So we have the product symbol with nc choose kc. And the denominator we already know. Okay, and there we have it. This is the hypergeometric distribution in the general case. Now often only two colors are involved, which means the whole thing here gets very simple. However, the simple case is also often known as the hypergeometric distribution. Therefore it might be worth it to write down the formulas for this special case as well. Of course the whole setup is the same, but we can make the sample space much simpler. The reason for that is that for two colors only one degree of freedom remains. For example, if we draw n boards and we count the number of red boards, which means the number of ones, we immediately get the number of green boards, which means the number of zeros. Hence, if we just count the ones, we can say a sample is just a number. This means that we can take the sample space omega as a set 0 to n. And then of course we can also simplify the probability mass function here. So let's look at p of the singleton k and copy what we already know. Which means we have n choose n in the denominator, and in the numerator we have two factors. Now here k1 is simply our k, and k0 is n minus k. And also we don't have to write capital N0 here, because we can use capital N minus capital N1. And there we have it. This is the compact formulation for the hypergeometric distribution when we only have two kinds of boards. Now for the last part of this video, let me show you how you can find this distribution in R. It's simply given by R hyper, so let's look at the manual here. So you see, this is the hypergeometric distribution, and if we scroll down, you see R hyper and all the variables here. The arguments are explained below, and this k here is actually our lowercase n. And you also see the other variables stand for the number of white boards and the number of black boards. So in our formulation this would be capital N1 and capital N0. And additionally we have the first argument for the number of repetitions. Therefore I would say let's see what happens when we have one observation, 9 white boards, 3 black boards, and we pull 5 boards out. Then when we hit enter we see our outcome. So the number of white boards we got is just counted. Okay, then let's repeat the whole random experiment. So here we got 3 white boards, which means we got also 2 black ones. Okay, so now maybe we can use the first argument to do a lot of repetitions of this random experiment. So let's say we do 20. So there you see we have a lot of 4s, but not a 2. However, we know that 2 is possible. Therefore maybe let's go to 200 observations. And there you see we find some 2s, but they are very unlikely. Hence to visualize that, let's put it into a histogram. So we put hist in front and close the parentheses and hit enter. The first thing we note is it's not the best visualization for a histogram yet, but we already have that 2 is very unlikely. Now one possibility to make the whole histogram nicer is to tell R where it should put the bins. And these breakpoints we can put into a vector x. So let's choose steps of 1 where we start at 1.5 and end at 5.5. So let's hit enter and there you see our x. And this vector x is now what we can put into the histogram function as an argument. This is not so complicated. We choose the histogram function and then we put in, comma, and breaks. And then this breaks should be equal to our vector x. And there you can see, this is what comes out. So maybe let's repeat it to see immediately what can change. So it's almost the same, we have the same behavior, 2 is very unlikely, but 5 is more likely. Hence, maybe to be more precise, let's go to 2000 repetitions. And there we get this histogram. And then I want to repeat it again and again to see that we are very much stable here. So what you should see here is that for this example, the highest probability is at 4. And the lowest is at 2, so we don't have a symmetric distribution. This is the case because we take out a lot of bolts compared to the number of bolts of each kind inside the urn. Therefore, I would suggest play around with these numbers and compare the result with the binomial distribution we've already discussed. Okay, then I think it's good enough for today, and I hope I see you in the next video. Have a nice day. Bye.